So in chapter 21, we're discussing carboxylic compounds, or compounds containing either a carboxylic acid or a carboxylic acid derivative. So carboxylic compounds are defined as groups that contain an acyl group bonded to an atom X, which is typically an electronegative atom or a leaving group. These include your acyl halides, your anhydrides, your esters, amides, thioesters, and acyl phosphates. So in each case, we have an acyl group bonded to an electronegative atom or leaving group X. And in this chapter, we're going to discuss the different reactions for these carboxylic acid derivatives, and we'll talk about methods to name and classify these carboxylic acid derivatives. Okay, so let's start with naming conventions for acid halides or acyl halides. So first, for most carboxylic acid derivatives, you first name the compound using carboxylic acid nomenclature rules. From here, you replace the suffix ic acid with the YL suffix, and then you specify the name of the halide. If you have a carboxylic acid that's attached to a cyclic system, you replace the carboxylic acid ending with carbonyl, followed by the name of the halide. For example, if we have a parent carboxylic acid of acetic acid, we would replace the suffix for acetic acid with the YL suffix, and then because this is an acyl chloride, we specify the halogen using the suffix chloride. Does this make sense to everyone? Let's look at another example. So suppose in this case we have benzoic acid. We replace the suffix, and that gives us benzoyl bromide. Now, where things get a little bit interesting is when you're looking at acyl chlorides that are attached to a ring. If we're looking at our parent carboxylic acid, in this case, this would be cyclohexane carboxylic acid. In this case, we replace our suffix with carbonyl chloride to denote the fact we have an acyl chloride attached to our parent chain. Do these conventions for naming carboxylic acids make sense to everyone? Okay. So let's try to apply what we've learned now, and let's try to name the following compounds, A and B. Keeping in mind that acyl chlorides, just like carboxylic acids, are very high priority functional groups. And as such, they're named and numbered preferentially with the lowest possible locant number. Further, just as a reminder, if you have a carbonyl, be it from a ketone or aldehyde, you use the oxo prefix. So let's take a look at these compounds, and let's try to name these compounds following IUPAC nomenclature methods. And I'd like students to share their proposed responses in the chat, verbally, or annotated directly on the class whiteboard. Just as a reminder, the principal methods in terms of naming and numbering these carboxylic acid derivatives starts from the naming and numbering rules for carboxylic acids. So, looking at either compound A or B, does anyone have any thoughts or observations that we should note for naming this compound? Are there any stereocenters in this molecule? Are there any functional groups we need to name? Or would anyone like to propose some carbon locant numbers? So, let's work through this example, and if there are any questions that I can address to help advance our discussion, don't be shy to ask them in the chat or verbally. I'd like to see some proposed student responses so I get a sense of how the class is progressing through this content and if there are any parts that I can provide feedback and clarification on. So we have one student immediately looking at this alkene and saying that alkene has stereochemistry. What is the stereochemistry for this alkene? Is it Z or E? E, exactly right. Okay. So with this information in mind, would anyone like to try to put together the name into a full IUPAC name? Would anyone like to try to propose a full IUPAC name? Or is there a question I can address as you're putting together the IUPAC name for this first compound? So we have students and we see a lot of outpouring in the chat for the correct stereochemical assignment. Would anyone like to try to propose a name for this first compound? So we have a locant number of 1 for our acyl bromide carbon, okay. So we have the following proposed locant numbers for the longest chain containing our acyl bromide. So would anyone like to try to propose a name for this? So we have a student proposing a name of E22-dimethyl pent 3-ene. So rather than acetyl bromide, so if we had the carboxylic acid, then the ending would be pent 3-enoic acid. And as a reminder, we replace the IC acid ending with YL followed by the halide name. So with that in mind, carbonyl bromide applies to cyclic species. So 2,2-dimethyl pent-ene, and then how do we write the end for this? How do we revise the end for this name? So it would be pent 3-enoic acid, but because we're dealing with an acyl halide, would anyone like to write out the name? So we replace the IC acid ending with YL followed by the halide name. Would anyone like to try and complete the name for this compound?
Is it acetyl bromide?
So you're on the right track, but you don't have to even say acetyl. We just write pentenoic acid, we highlight the IC acid ending, and we just replace it with YL followed by bromide. So it would be pentenoyl bromide. Does that make sense? All you're doing is you're replacing the IC acid ending for your typical carboxylic acid name with the YL suffix followed by the halide name. Notice it's not enyl bromide, but enoyl bromide. Does that make sense? Now, looking at this name, does anyone have another comment? Is there something missing from this name? We have to specify the locant number for our stereocenter. So this would be 3E, because our alkene is at position 3, 2,2-dimethyl. Remember, if we have two groups, we have to note the locant number of each to avoid ambiguity. Pent, 5-carbon chain, 3-ene, alkene at the 3 position, oil, because we have an acyl halide, bromide, because it's an acyl bromide. Does that make sense?
I have a question about the oxo
Yes.
part.
Yes.
So that shouldn't be incorporated.
Not in this case, because we don't have any carbonyl substituents. The reason why I brought up this statement is because if you're working on question B, where we have an aldehyde and an acyl chloride, the aldehyde is lower priority. So we have to name this carbonyl substituent using the oxo prefix.
Oh, okay, that makes sense.
Perfect. Perfect.
Thank you.
So, any questions on this first example before we move on and we tackle this second problem? Let's try to apply what we've learned now, and let's try to name this second compound. So let's take a few minutes and let's try to name this second compound. And if there are any questions, or if you would like to share your proposed responses, don't be shy to share your questions or proposed responses in the chat, verbally, or written out directly and annotated onto the class whiteboard. So let's work on this example for about another 2 to 3 minutes. And then I'd like students to share their proposed responses in the chat, verbally, or on the class whiteboard. So, are there any questions that I can address to help advance our discussion? We have a proposed name for this compound of 4-hydroxy, 5-oxo, exactly right, pentanoyl chloride. What does the class think? Do you agree with this name? Do you disagree with this name? So aldehyde substituents on a ring are called a formal group. An aldehyde substituent as part of a chain is named like a carbonyl with the oxo prefix. Does that clarify? So we notice a large amount of class consensus for this proposed name, and this proposed name is perfectly reasonable. Any questions on this proposed? Any questions on these two examples? Any questions I can address before we move on to the next example? Okay, so let's try to name this next compound now. In this case, we have an acyl halide that is attached as a substituent on a ring? So let's try to work through this example, and let's spend about another 2 to 3 minutes trying to propose a name for this compound. And then I'd like students to share their proposed responses in the chat or verbally. And if you have any questions I can address to advance the discussion, don't be shy to ask them in the chat or verbally, and I'd be happy to provide input and feedback.
Professor, would that iodine be referred to like as iodo, or would it be referred differently in this case?
So this would be acetyl iodide.
Iodide. Okay.
Yeah.
Thank you.
Because even though it's an iodo is used as a iodo is used as a prefix when it's a substituent. So for example, this chlorine would be named as chloro, a chloro substituent. However, if it's part of an acetyl iodide, if it's part of this group, then you name it with the iodide suffix, partially because we're noting that partially the name's derived from the fact that the leaving group on this acyl halide is the iodide ion. That's one way I like to remember it. Does that make sense?
I think so. So when it comes to naming it, would it be 4-chloro-cyclopentane carbonyl iodide or acetyl iodide?
So we have 4-chloro-cyclopentane. So let's look. So when we're talking about cyclic systems, we name it as carbonyl followed by the halide name. So you said carbonyl
Iodide?
Yep, that looks reasonable. Yep, that looks perfectly reasonable. However, we have one thing we need to note, the stereochemistry. Yes, and also the locant numbers. So looking at the locant numbers, the chlorine would likely be at the 3 position instead. And we have another student in the chat noting that these stereocenters are 1s and 3s. It's common to put the 1 locant number before the carbonyl iodide, but it's partially redundant in that the locant number for your acyl halide, in this case your carbonyl iodide substituent, will always be at carbon 1. So looking at this example, do we agree with our stereochemical assignments? Do we agree that both of these stereocenters are S stereocenters? What do we think about that? As a reminder to discuss the locant numbers, we count in a way to give us the smallest possible locant numbers. We have a lot of students showcasing or noting their agreement with the proposed stereochemical assignments. It's always important that you justify your assigned stereochemistries. Okay, so your acetyl iodide is priority 1, the alkyl chlorides priority 2, the normal alkyl groups priority 3. So tracing, we're going counterclockwise. So that's an S stereocenter. Chlorides priority 1, alkyl iodides priority 2, normal alkyl groups priority 3. Tracing, we're going counterclockwise. So that gives us an S stereocenter. So based on this, our assigned locant numbers, stereochemistry, and full IUPAC name for this compound look completely reasonable. Does this make sense to everyone? Any questions before we move on? Okay, so let's keep going now and let's talk about methods for naming anhydrides. So first, you name your compound using carboxylic acid nomenclature. If the anhydride is symmetrical, as in both of the carboxylic acid components used to make the anhydride are identical, you name the anhydride by replacing the acid suffix with anhydride. So for example, if we have propanoic acid, it would be named as propionic anhydride. Now I admit that this example is a bit odd because propionic anhydride is a bit of an informal name. You can also call this propanoic anhydride, though propionic anhydride is far more common as the colloquial common name for this anhydride. Another example that we've seen previously is this compound. Does anyone remember the name for this compound derived from acetic acid? We've seen this in the previous lab when we prepared acetamide. Does anyone remember the name for this compound that I just drew out? Derived from acetic acid, it's acetic anhydride. Anhydride, loss of water. Does this make sense?
You said loss of water, like could you go more into depth on that?
Yes, we'll actually talk about this later on in this
Okay.
chapter when we talk about the synthesis of an anhydride. But essentially, do you notice how in the anhydride, we have two carboxylic acid fragments, but we've lost an equivalent of water. We've lost one of our oxygen atoms when we formed our anhydride. Does that make sense?
Yeah, I see.
We'll talk about the mechanism for that as well later on in this chapter. Now, where things get a little, you can call it ethanoic anhydride. The propionic anhydride name is more of a colloquial name. So in this case, if your anhydride's asymmetrical, you have to name the two parent carboxylic acids alphabetically, then you replace the acid suffix with anhydride. So for example, this compound would be acetic acid, benzoic acid. So we call this acetic benzoic anhydride, derived from acetic acid and benzoic acid. Do the naming rules for asymmetrical and symmetrical anhydrides make sense to everyone? Okay, so let's keep going now and let's try to name the following compounds. And just as a modification, let's add a carbon to get a new anhydride. And let's try to name this new anhydride. So let's take a few minutes and let's try to name these compounds following IUPAC nomenclature rules. And I'd like students to share their proposed responses in the chat or verbally. And if there are any questions that I could help address to advance our discussion, don't be shy to send them my way. One thing that I would note is that computers may use an alternative method for naming these anhydride compounds. So it's important that if I ask you to name a compound, you follow the conventions associated with the class for any class examples. So Would anyone like to try and name anhydride A or B following the naming rules for anhydrides? So we have a proposed name for the first compound derived from butanoic acid. So this would be butanoic anhydride. Yep, exactly right. Derived from the parent 4-carbon carboxylic acid, butanoic acid. Does this example make sense? Okay, would anyone like to try to attempt to name compound B? Would anyone like to try to name this asymmetrical anhydride? So we've noted this acetic acid derived side chain. We have a pentanoic acid derived chain. So then alphabetically acetic is before pentanoic. So we'd name this as acetic pentanoic anhydride. Does this make sense? Any questions on naming anhydrides?
I have a question. I realized that for A, it's a is it butanoic?
Yes.
Oh, so it wouldn't be butionic, like with the BU. Hold on, I don't even know if I'm making sense.
Yeah, you name it just like butanoic acid, except rather than using the acid suffix, you name it with the anhydride suffix. So rather than butanoic acid, it would be butanoic anhydride. So there's no other change to the name besides the suffix. Did that answer your question?
Kind of. So like the whole ionic ending wouldn't be added to this one.
Yeah. Propionic acid is a colloquial name.
Okay.
Does,
Okay.
does that answer your question?
Yeah.
Perfect. Any other questions on these examples before we move on? Okay, let's talk about the next subclass of compounds, and these are amines. So for amines, you name the compound again using carboxylic acid nomenclature rules. There are two cases for amines. If the amine is unsubstituted, you replace the oic acid or ic acid suffix with the amide suffix, or you replace the carboxylic acid suffix with carboxamide, and this occurs if it's a substituent on a cyclic chain. If the nitrogen is substituted, you identify the substituent groups using the locant number or locant letter N, and then you name the parent amide. So for example, acetamide is derived from acetic acid. Hexanamide is derived from hexanoic acid. Cyclopentane carboxamide is derived from cyclopentane carboxylic acid. Does that initial idea make sense? Now, if your amine is substituted, we name and note each substituent on our amine using the locant number N or locant letter N. So in this case, if we have a methyl group on our nitrogen, we name this as N-methylpropanamide. Treat this N similar to the locant numbers for substituents. In the event we have two substituents, we name this as NN. Since they're the same, we can call this NN diethyl cyclohexane carboxamide. Does this method make sense? Any questions on naming amides? Okay, let's keep going then. And let's try to apply what we've learned to name a few of these compounds. We have compound A and B. Let's take about 4 to 5 minutes and let's work on naming each of these compounds using IUPAC nomenclature methods. And I'd like students to share any questions or proposed responses that they have in the chat, verbally, or annotated directly onto the class whiteboard. And I'd like students to ideally share their proposed responses so we can have a robust discussion. So let's start with this first compound. The N is just indicating that we have a substituent on nitrogen. And just like any other case where we have substituents, we name our substituents alphabetically. So, does anyone have a proposed response, or are there any questions that I can address to help advance our discussion? Any questions that I can help address? So let's try to get some proposed responses in the chat verbally, or if there are any questions that I can help answer to help advance our discussion, don't be shy to type your questions in the chat, and I'd be happy to provide input and feedback. So, does anyone have a proposed name for any of these two compounds? So we have a few proposed names in the chat. So we have, so looking at this, we have an isopropyl and a methyl group. So we'd name this as N isopropyl, N methyl, 1, 2, 3. I'm still transcribing the names. The chat's moving a little quickly. 3-hydroxy butanamide. The oxo prefix isn't necessary because this carbonyl is part of your amide. We have one student noting 3R. This configuration is a stereocenter, so we need to note the R or S configuration. So one question that I have is looking at hydroxy, methyl, and isopropyl. Are these substituents arranged in alphabetical order? are these substituents arranged in alphabetical order? Not yet, right? Hydroxy H is first alphabetically. So this would be 3R, 3-hydroxy, N-isopropyl, N-methyl butanamide. Does this proposed name make sense to everyone? Any questions on this example? You can't use the NN grouped locant number unless it's the same substituent. It's only in the event where you have repeated identical substituents. And that's a good lead into our next example, actually. So let's look at structure B, and let's try to propose an IUPAC name for this compound. And I'd like students to share their proposed responses in the chat or verbally. And if you have any questions, don't be shy to share them in the chat or verbally, and I'd be happy to provide my input and feedback.
So the N groups don't necessarily have to be like in the front, just.
Not necessarily. It's based on alphabetical order.
Okay, gotcha. Okay, thank you.
Think of it like just another locant position. So just like we use locant numbers for all of our substituents before the name, the N location just says this substituent is on our nitrogen. Does that make sense? So would anyone like to propose a name for compound B?
Can you repeat what you said about the oxo again on the earlier example, that it's not
So
necessary?
the oxo prefix only occurs if you have another substituent besides our amide. So if we had another carbonyl in this structure, then we would use the oxo prefix. Since the amide is the only substituent with a carbonyl, the amide suffix already denotes that we have a carbonyl and we already have the amide. Does that make sense?
Okay, yeah, thank you.
So let's keep working through this example. Does anyone have a proposed name for this compound? Would anyone like to share a proposed name for compound B, where we have an amide attached to a cyclic ring? So we have a proposed name of 1R, 2R, 2-bromo, N-N-dimethyl, cyclohexane, carboxamide. What does the class think for this proposed name? You can even name this as cyclohexane 1-carboxamide, though that's slightly redundant. Would anyone like to share Would anyone have a suggestion for any revisions or modifications to this proposed name? I'm going to draw out a rotated structure for a moment. Generally, just like with carboxylic acids, the carbon attached to your carboxylic acid group, amide, or other carboxyl derivative will always get assigned locus number 1 for cyclic systems. Does that make sense? So looking at the stereochemistry, does anyone have a revision for the proposed stereochemical assignment?
Well, I was just wondering if when we're looking at number 1,
Yeah.
like wouldn't the bromine technically have higher priority because they're both
That's
like 1
correct.
carbon away?
Yes, the alkyl bromide is higher priority. Bromine beats oxygen in terms of priority. Tracing, this would give us 1s, 2r. To provide justification for our second stereochemical assignment, bromine's priority 1, amide side chains priority 2, alkyl side chains priority 3. That gives us a 1s, 2r configuration. Does that make sense to everyone? Does this example make sense? Any questions on structure B's naming convention? Okay, let's look at this last compound. Let's try to apply what we've learned from naming amines to propose a full name for the following compound. So let's take a few moments and let's try to name this compound using IUPAC nomenclature methods. And if there are any questions I can address as we work through this example, don't be shy to send them my way, and I'd be happy to provide my input and feedback. So let's try to get a few proposed responses from students in the chat, verbally or annotated directly onto the class whiteboard. We already have our first proposed name, N-ethyl. Cis and trans is reserved for cyclic systems. I would explicitly note the configuration using RS nomenclature as it's less ambiguous. We have 3 methyl groups at 3 different positions. So since we have 3 methyl groups, we may want to use a certain prefix. So we have a student proposed name of N-ethyl, N-methyl, 2,3-methyl pentanamide. Pentanamide. Okay. Z and E refers to alkenes. So I would note the stereochemistry of each position using R and S nomenclature. So the student proposed name has many good things about it, but it needs to be revised slightly. would anyone like to offer a proposed revision to this?
Question.
Yes.
So for these, because I wanted to make sure about the whole trans thing. So it's not a good idea to use the trans and the cis for this, more of the stereochemistry.
This in trans does not give us absolute stereochemistry, it gives us relative stereochemistry. It's acceptable for cyclic systems in most cases. However, for acyclic systems, R and S notation for configuration is more precise.
Okay. Alrighty. Yeah,
Perfect.
thank you.
So the numbering convention assigns a locant number of 1 to the amide carbonyl carbon. And from there, we number down our chain to give us the longest possible chain attached to our amide. So, would anyone like to offer a revised name for this compound?
Wait, I'm sorry, I missed it. What did you say about the stereochemistry?
The stereochemistry for acyclic systems need to be explicitly noted using RS notation.
Oh, okay, so we're just working on the stereochemistry right now.
Stereochemistry and revising the name to more appropriately phrase this proposed name, because we have 3 methyl groups and we can group these methyl groups together by grouping their locant numbers and using a prefix. So if we have 3 methyls, it would be trimethyl.
Would we do like N2,3 trimethyl? Like,
Exactly right. So this is N-ethyl, N2,3 trimethyl. Yeah, it's sort of weird to say, but N functions exactly like a locant number. So we have N-ethyl, N2,3 trimethyl, and then what?
is it still the pentanamide?
Yep, exactly right. Noting that derived from the name pentanoic acid, it's pentanamide with an amide, A-M-I-D-E suffix. Does that make sense? We need the stereochemistry. Yes, exactly right. So would anyone like to propose the stereochemistry for these 2 stereocenters along with the locant numbers for each stereocenter? Would anyone like to share their proposed stereochemical assignments? Let's take a few minutes to work through that. Are there any questions that I can address as we work through this example? Would anyone like to share their proposed stereochemical assignments for these 2 stereocenters? That would help us complete this problem. So we have an assignment of 2R3S. Okay, let's take a look. So for each of these stereocenters, the amides, priority 1, this long alkyl chains, priority 2, methyls, priority 3, tracing, that gives us an R stereocenter. For our second stereocenter, the amide chain is priority 1, the ethyl chain's priority 2, methyl's priority 3. So tracing, that gives us an S stereocenter. Yep, so we now have a full IUPAC name for the following amide. Does this make sense to everyone? Okay, so let's keep going then, and let's talk about the naming rules for thioesters. So when dealing with thioesters, first you name the thioester R group, you name the compound using carboxylic acid nomenclature, and then from here you replace the oic acid or ic acid suffix with thioate, or if you have a cyclic system and your thioester is attached to a cyclic ring, you replace the carboxylic acid suffix with the carbox or carbothioate suffix. So for example, if we have our parent carboxylic acid acetic acid, we name this as methyl because we have a methyl group attached to our sulfur atom, then thioacetate. To note, we have a thioester derivative of acetic acid. Does that make sense to everyone? Another example is if we're looking at the derivative of butanoic acid, we have an ethyl group attached to our sulfur. So this would be ethyl butane thioate. Finally, if we're looking at a thioester attached to a cyclic ring, we first name our group attached to sulfur. So we name this as methyl cyclohexane carbothioate. Do these naming conventions make sense to everyone?
So for the cyclic one, we have to mention the carbo part.
Yes, so just like we would name a carboxylic acid attached to a cyclic chain as carboxylic acid, we name our thioester attached to a cyclic system as carbothioate. Does that make sense? Perfect. So let's try to apply what we've learned to the following examples. So let's make this a ethyl thioester. Okay, so let's work on these two examples, A and B, and let's try to propose IUPAC names for each of these compounds. So let's take about 3 to 4 minutes to work through these examples. And if there are any questions or proposed responses I can address, don't be shy to ask them in the chat or verbally, or send your proposed responses in the chat or verbally, and I'd be happy to provide my input and feedback. So we have a proposed name for this first compound as methyl butane thioate. Yep, and that proposed name looks completely reasonable, and we see quite significant class consensus. Would anyone like to propose a name for this second compound? Working through these naming problems, would anyone like to propose a name for this second compound? Generally, the way that you name these compounds is you name your sulfur substituent first, then you name the carboxylic acid derived chain second. So any groups on your sulfur atom will get priority in terms of naming. So you name the sulfur substituent first. Does that make sense? So with that in mind, would anyone like to try to propose a name for this compound? Or is there a question that I can address to help advance our discussion? So we have a proposed name of 1R2S ethyl cyclopentane 2-hydroxy carbothioate. Perfect. That name looks reasonable. What does the class think about the stereochemistry of each of our stereocenters? Okay, so to justify our stereochemical assignments, thioesters priority 1, hydroxyl side chains priority 2, alkyl side chains priority 3. In the second case, hydroxyl group is priority 1, thiol side chains priority 2, or more correctly, thioester side chains priority 2, alkyl groups priority 3. That's an S stereocenter. So this proposed name looks completely reasonable. Does anyone have a question on these examples?
So for this naming part, that cyclopentane part is allowed to come first before like the 2-hydroxy because of alphabetical order or because of how this is supposed to be.
Oh, I just noticed that's an important thing to discuss. The hydroxy should be first. The ethyl comes first because it's the sulfur substituent. Then we name our substituents on the carboxylic acid derived side chain. So that would be 2-hydroxy, then cyclopentane, and then the carbothioate suffix.
Okay, that makes more sense.
The name I transcribed and the second name the student proposed, the name that I was looking at in the chat was correct, but the name I transcribed initially had them flipped. Yeah, so now this corrected name is perfect.
Okay, got it. Thank you.
Any other questions? Okay. So then, let's talk a little bit about common reactions and patterns of reactivity of these acyl group derivatives. And we'll be talking about the general class of reactions known as nucleophilic acyl substitution reactions. In this case, a tetrahedral alkoxide intermediate is formed during 1,2 addition into a carbonyl. So if you have a nucleophile, it attacks your carbonyl, and you end up making a tetrahedral intermediate. From here, it will collapse and we can kick out our leaving group in a substitution pattern. When we have aldehydes and ketones, we just saw addition. There's not really a viable leaving group, as hydride and alkyl groups generally don't leave. So aldehydes and ketones favor addition products. Carboxylic acid derivatives often have an acyl carbon bonded to a leaving group, and thus the leaving group can be expelled to generate a new carbonyl compound, leading to substitution products. Carboxylic acid derivatives generally yield substitution products. So, aldehyde or ketone, we see addition. We've seen this with cyanohydrin formation, hydrate formation, etc. When we have carboxylic acid derivatives, we see nucleophilic acyl substitution, where we can kick out our leaving group. One thing to note, one thing that I would like to mention is when we think about whether a substitution reaction will occur, it's important that we think about the leaving group capability of our leaving group. And we'll talk more about that later on in this chapter. Okay, one thing that we need to get out of the way immediately is that carboxylic acid derivatives, along with aldehydes and ketones, do not necessarily react with nucleophiles at the same rate. First, nucleophiles generally react more readily with unhindered carbonyl groups. The more substitution we have adjacent to our carbonyl, the slower the rate of addition. We've seen an example of this already when noting that these sort of neopentyl chlorides are surprisingly recalcitrant and surprisingly difficult to react in substitution reactions. Why? The position adjacent to our reactive carbon is heavily hindered. And as a result, the reactive carbon, just like in these substituted ketone examples, is more hindered. And as a result, the reaction's slower. Does this make sense to everyone? This idea that substitution at the alpha position increases the steric hindrance around the carbonyl carbon, which in turn leads to a slower reaction. Does this idea make sense to everyone? Does this idea make sense? Okay, so let's try to apply what we've learned and let's answer the question, which of these substrates, A or B, would have a faster rate of reaction with phenylmagnesium bromide? So what does the class think? Substrate A or B? We have a lot of students typing B. Why?
Because it's a little hindered.
Yep, exactly right. It's a less hindered ketone, and as a result, it's more reactive. Does this example make sense to everyone? Okay. So then, let's keep going then. When we think about the relative reactivity of carboxylic acid derivatives, generally more electrophilic carbonyl groups are more reactive to addition. This is why acyl halides are your most reactive carbonyl derivative, while amides are the least. Generally, the intermediate with the best leaving group undergoes collapse and loss of the leaving group the fastest. So in terms of substrates, our most reactive substrates are your acyl halides. These typically are very hard to isolate if you're using any sort of equilibrating process. On the other hand, our amides are the least reactive carboxylic acid derivative. And as a result, they're generally quite stable to many carbonyl substitution conditions. Does this idea of relative reactivity make sense? To really help us understand what's going on here, if we look at our halide, so we have something like chloride. For the anhydride, our leaving group is the acetate ion. For an ester, we'd be kicking out an alkoxide. For a carboxylic acid, we'd be kicking out hydroxide or the O2 minus anion. And for amides, we'd be kicking out an amide anion. So looking at these groups, which of these leaving groups would we argue is the best leaving group? Which of these anions listed is the best leaving group by far? Which of these anions would be considered the best leaving groups? The halide, right? So we see generally the more reactive carbonyl derivatives and carboxylic acid derivatives generally have the best leaving group attached to your carbonyl carbon. Does this idea make sense to everyone? Okay, so let's delve into this idea of leaving group capability to help us understand why acyl chlorides are more reactive. If we think about leaving group capability, often a pKa table can serve as a way to gauge the suitability and ability of a group to serve as a leaving group. So as we see, generally, by looking at the conjugate base, the less basic and less nucleophilic the conjugate base is, the more readily that anion will leave and serve as a leaving group. So your halides and acetate ions are weak bases and are great leaving groups. Comparatively, hydroxide, alkoxide, and amide ions are terrible, terrible leaving groups because the resulting leaving group is not only highly basic, but it's quite nucleophilic as well. Does this explanation make sense to everyone?
Mind scrolling down a little bit so I could see the leaving group part
Here?
or up. Sorry, all the way up. Yeah, right there.
Okay. Any other questions that I can help address? Okay, so let's keep going now and we can tie this back to this general hierarchy for substitution reactions. Generally, we can convert a more reactive acid derivative into a less reactive species. Reactions in the opposite direction are possible, but require more complex approaches. Generally, if we want to activate our leaving group, we have to use additional reagents to activate our substrate for carbonyl substitution. We'll see examples of this, including, for example, reaction of a carboxylic acid with thionyl chloride. So generally, it's quite easy to displace a good leaving group with a reasonable nucleophile. It's more difficult when you have, for example, an amide, where you're displacing a very poor leaving group. Does this idea and does this hierarchy of reactivity make sense? Okay, so generally, if you want to prepare a more reactive carboxylic acid derivative, the leaving group has to be activated for substitution. So for example, treatment of a carboxylic acid with thionyl chloride would generate this activated chlorosulfonyl group, which can then be readily displaced with chloride. Notice how we have activated our alcohol as a leaving group using reagents such as thionyl chloride. This is a common pattern for many carbonyl substitution reactions where the leaving group is activated via either protonation or reaction with an added reagent. Does this make sense to everyone?
What is the point of the arrows on the carbonyl?
Just to showcase like a substitution. It's just a shorthand to show that because we've activated this alcohol as a leaving group, we can now readily displace it in carbonyl substitution reactions. And it's essentially just to show that chloride can now displace this chlorosulfonyl group because we've now activated our alcohol.
Okay, so on the arrows on on the left carbonyl, does the double bond like go up and then the electrons, the lone pairs go down?
Do it in a more stepwise manner, just to make that part explicit. Chloride will attack. We'd make a tetrahedral intermediate, just like for every carbonyl substitution mechanism. From here, this tetrahedral intermediate can collapse.
Oh, I see.
And now this time, because we're considering leaving group capability, this chlorosulfonyl group is actually a reasonably competent leaving group, and thus it's kicked out preferentially compared to our halide.
Okay, I see now.
Does that make sense? Did that answer your question?
Yeah, thank you.
Perfect, perfect. So let's try to apply what we've learned here, and let's try to rank the following compounds A and B in order of increasing reactivity. So which of these two compounds would be more reactive for carbonyl addition or substitution reactions? A, exactly right. Generally, aldehydes are way more reactive than ketones. Exactly right. Perfect. So let's take a look at this next set of compounds that we'll label A, B, C, and D. And I'd like us to repeat this ranking process. Let's try to rank these 4 compounds in order of increasing reactivity in carbonyl substitution reactions. Keeping in mind, and this is important, that the reactivity of different groups for carbonyl substitution reactions depends on the ability and capability of our leaving group. So we have a proposed ranking of A, D, B, and C. So we have chloride, an alkoxide group, an amide, and an acetate group. And as we see, chloride's the best leaving group, followed by acetate, followed by ethoxide, followed by dimethylamide. So this proposed ranking of reactivity looks perfectly reasonable. Does this make sense to everyone? Does this idea of the relative reactivity of different carbonyl groups and carboxylic acid derivatives make sense? Okay, so let's try to apply what we've learned to another example. So keeping in mind, we can look at a range of different leaving groups, and by comparing their leaving group capability, we can even rank carbonyl compounds that we haven't directly seen before in order of increasing reactivity. So let's take a look at the following example. And let's try to rank these 2 compounds in order of increasing reactivity. So we have a lot of students typing A, right? So if we compare these 2 leaving groups, we see that this first leaving group is stabilized via resonance, and thus the leaving group on carbonyl compound A is a more effective leaving group, and thus carbonyl compound A is more reactive to carbonyl substitution reactions. Wonderful, wonderful. Does this idea and do these examples make sense to everyone?
Is the idea of thinking of it that it kind of has like this kind of similar properties to anhydride be an incorrect way to look at it?
It's very similar to anhydride, yes. It's the amide equivalent. These are called amides.
Okay. Alrighty, thank you.
Any other questions on these examples? We're just about at the end of today's scheduled lecture period. So does we have any last minute questions before we archive today's recording? Any last minute questions I can address? If not, what we'll do is we'll archive today's recording